section 11.4 is all about comparison. We have two tests in this section called the comparison test. So let's start with what is called the comparison test. Sometimes I refer to it as the direct comparison test once we work with the other comparison test called the limit comparison test. Sometimes I will actually refer to this guy as the direct comparison test. So we have CT for short, or DCT for direct comparison test. And so this guy uses two series, A sub k and B sub k, and they have to have positive terms. So that is something that's important. So keep that in mind. To use this series, we have to have positive terms. To use this test, we have to have positive terms in the series. And then the condition for convergence is that if A sub k is less than or equal to B sub k for all k greater than or equal to n, and the larger series converges, B sub k converges, then A sub k must also converge. And I'm noticing here that for whatever reason, the I of my if has like blipped off of the screen or out of the table here. So let's just squeeze that in there. If the smaller series diverges, if A sub k diverges, then B sub k must also diverge. So that should intuitively make sense, right? If you're smashing a series underneath a converging series, then the series underneath must also converge, and reversing that, if you have a series that has been pushed above a diverging series, meaning it's always greater than a diverging series, then that larger series must also diverge. So just a couple little comments on this one. If you have a series that you're looking at and you want to use comparison, you need to compare it to something that you know converges or diverges. So the two series that we will be kind of working with here, the two that we can know through previous sections, converge or diverge, and that's our geometric or our P series, so we can compare to those. Okay, so let's jump right into a couple examples in this video, and then talk a little bit about the limitations of the comparison test and why we might want another way to compare. So let's start with this one. This is the series from k equals 1 to infinity of 1 over 3 to the k plus k. And when I'm looking at this one, I'm thinking to myself, right, I got to figure out what am I going to compare to, right? So the question has to come up, what should we compare to? So what should we compare this series to? And when I'm doing that, I go through kind of this visual test, and I'm looking here. The numerator is simply 1. In the denominator, we have an exponential, and then we have a constant. Well, this exponential is going to dominate. This guy dominates the bottom, meaning it's just so much larger, right? It grows at such a faster pace than the simple k, the simple linear addition of k. We've got an exponential function. We're letting k go to infinity. 3 to the k, the exponential is going to dominate the denominator. So in my mind, when I'm looking at this series, I'm thinking, well, this looks an awful lot like the series 1 over 3 to the k, from k equals 1 to infinity. Or another way to think of it is, as it approaches infinity, it's going to behave an awful lot like 1 over 3 to the k. Has that a little addition of k, but beyond that, it's going to behave an awful lot like that 1 over 3 to the k, since 3 to the k is going to dominate. Okay, so that's the thought process, and then I come in and I say, okay, let's actually use the comparison test. So to apply, so you're going to pick a series to compare to. So what should we compare this to? Find the series you want to compare it to. So that's our first step. Find the series to compare. And just a little note, think in terms of, useful series. The useful series that we know will converge or diverge by observation or from previous proofs. Use series we know a lot about. So just geometric or P series. Now you can use another series, one that you could easily apply integration test to or divergence test, something like that, but that's what you want to do. All right, so figure out what should we compare it to. find a series to compare. So that's our first step. Figure out what is it that we're going to actually, excuse me, compare to. Then the second step is to apply the test. So we have to set up the proper inequality. So if we can just go back to the test here, we have to set up our inequality. We've got to show that one of the series is less than the other series, or vice versa. One of the series is greater than the other series. So now we have to set up, we actually have to compare the terms in the two series by using an inequality. Okay, so we have to set up our inequality, a sub k. So remember, we have to show that one of the series is less than or equal to b sub k for all k greater than or equal to, I can't remember if I used a capital N or a little n in the, so greater than or equal to some value n. Little note on this one while we're here. This is saying that as long as, so note on this one, that we could, right, this is saying n, so we could actually say this is, it's eventually, this inequality will eventually, the inequality will eventually this idea of eventually, it might not happen always, it might not happen until you get to the 100th term, but as long as this inequality eventually holds, then we can apply the comparison test. So the inequality will eventually hold for all k greater than or equal to n. Okay? Okay, so that's kind of a little side note. It might be that it's true always, but it could be that it takes the first 5 terms until that inequality holds, and then it holds after that. One other thing that we need to add on to this is these terms also have to be positive. So these terms have to be greater than or equal to 0. You could have some 0 terms too, but these terms have to be greater than or equal to 0. So we have to also guarantee that we have positive terms. So positive terms. The comparison test works only for series that are positive. So we have to have positive terms and hold this inequality. All right, so what should we compare it to? We already know what we want to compare it to, and now we actually have to get in there and do the comparison. So we already picked what do we want to compare it to, so now let's get in here and actually set up this inequality, or see if we can set up this inequality, because it might be that we can't. So let's start with this. So if we're going to compare, so here's setting up the inequality. So here's step 2, setting up, I'll put it next to set 2. We know what we want to compare it to, now let's set up the inequality. So for our inequality, what we're going to do is say this. Notice that if we were to take 3 to the k and add k, that is just by default, that has to be greater than 3 to the k for k greater than or equal to 1. Okay? I'm going to make a little note here. I kind of smushed so that they would all fit on the same line. I kind of smushed my steps in next to my example, so let's do that. Keep myself a little line here. Okay, so that has to be the case. If we take an exponential and we add something that is greater than or equal to 1, it's going to just by default be bigger than the exponential. So we know that. Then if we reciprocate those two values, the inequality will flip. So then 1 over 3 to the k plus k has to be less than 1 over 3 to the k. Okay? And what we should have said at the very beginning, or actually let's do it right here, is also note that these are also k is greater than or equal to 1. So these have to also be greater than 0, not even equal to. We're never even going to be equal to 0. So as long as k is greater than or equal to 1, we have the inequality that we need. Okay? Our terms are positive. Okay? And the series that we're looking is less than 1 over 3 to the k. Okay, So we compare the terms, set up the inequality. Then show convergence or divergence of the series we are comparing our series to. Oops. So now get in there and say, well, now that we've got this set up, we know what we wanted to compare it to, we've set up the inequality, now we need to show that we either have convergence or divergence. So what we're going to do here is, sorry about that, my next example is popping in there. Let's push that down just a little bit further. Now what we're going to do is we're going to come in here and we're going to say, well, would this series that we're looking at, this one that we wanted to compare to, and when we picked this series, and I kind of skipped over that so we could start writing the steps, but when we picked this series, this 1 over 3 to the k, we wanted to also sort of think about like, well, would that be converging or diverging? Like 1 over 3 to the k, what kind of series is it, right? We talked over here about useful series, geometric series, p-series, but are we going to be having convergence or divergence? When we pick this, is it something that we're going to be utilizing to show convergence or divergence? And so when we first picked this series, we should have also kind of thought about, oh, hey, that's a geometric series, right? That's a geometric series. That's got an R of 1/3. Well, 1/3 is less than 1, so that's got to be converging, right? Like this is kind of in my mind. I'm thinking, right? Here's my little thought bubble. Okay, I'm sort of thinking like, oh yeah, that is a geometric series. So that's we're kind of having that in my mind. And then when I go down to setting up that inequality, we've now shown that the series we're looking at is smaller than that series, which is perfect because that series that we're comparing to converges, but we need to actually officially set that up. So there's 2 steps that you have to show when you're applying this test. One of them is the inequality to what you're comparing to, and the second is proving or stating what the series you compare to does, if it converges or diverges. So now let's get in here. So here's our second step. We got the inequality set up. Now let's actually show convergence or divergence. So we can make a little statement like this. Something like, note that the series 1 over 3 to the k from k equals 1 to infinity is exactly equal to, and I'm just going to write it in the official geometric series form, 1/3 to the k is, we got to make this statement, a geometric series where r equals 1/3, which is less than 1, therefore, thus converges, therefore it converges. And then my final statement, since my series that I'm looking at is always less than that series, back to the highlighted inequality, I can actually go straight into the comparison test now. So I can say, all right, therefore, 1 over 3 to the k plus k from k equals 1 converges by comparison test. Now, this was what we call the direct comparison test, so I'll start to abbreviate here in the next examples that this is the direct comparison test. Okay? All right, and I just noticed, that's funny, I just noticed that I wrote a partial sentence over here. Started talking, I think, about our example. Show the convergence or divergence of the series we're comparing our series to. Oh, no, I guess that's not a partial sentence, but I just didn't put a period. That we're comparing our series to. Show whether it converges or diverges. Okay, so comparison test. You take a series, you figure out what do you want to compare it to, then you actually set up the comparison, you get your inequality. Let's underline that. So you get your inequality set up. Has to be in the proper form. So if you're trying to show a convergence, you have to show that your series is less than a converging series. If you want to show a divergence, you have to show that your series is actually greater than a diverging series. And then you talk about, or you show, the convergence or divergence of the series you want to compare to. Okay. And this will, let's do this, applying the comparison. Okay. Okay. All right, so those are the steps. I want to make one little note here that what if let's just come over here and say, take a look at that series real quick, and then let's just come over here for a minute and let's just say, what if the series that we looked at was almost exactly the same, right? We got 1 over 3 to the k plus k. What if I had something like 1 over, just slightly different? What if I subtracted k instead of adding k, right? Like it's almost exactly the same, right? But this has now changed to a minus. And what I would say on this particular one, I want to motivate the reasons for why we might want another test, right? So why do we need another comparison test? So why do we need another comparison test? Right? Like why do we even need another comparison test? Because the next video is going to be all about a second comparison test called the limit comparison test. But like, why would we even need that, right? Like why, if we have the comparison test, it works nicely. Why do we need another comparison test? So, and I want to talk about why that would be, right? What if we had this little minus? What if all we did was switch that minus right there, right? Well, I would still go through the exact same process. I would still look at this and I'd say, I'm going to compare this to that exact series that we just did, 1 over 3 to the k, which I know converges by geometric series, right? So in my head, I'm thinking, right, geo series r equals 1/3, which is less than 1. So I've got convergence. So that's my little thought bubble, right? That's going on in my head. I got that thought bubble. But then I have to set up the inequality, right? So that's my thought. I figure out, okay, I'm going to compare it to that guy. And then I go into and I go, okay, now I got to set up the inequality. Okay, and then I can talk about that convergence. But when I go to set up the inequality, check this out. 3 to the k minus k, well, that's always less than, right? Like that's we're subtracting, we're taking away something. That has to be less than the exponential 3 to the k for k greater than or equal to 1. Okay. Then I flip those inequalities, right? 1 over 3 to the k minus k is always going to be bigger than 1 over 3 to the k. And that is a problem for the direct comparison test because this guy, right, is bigger, right? We've got a bigger series. This guy converges. We know that converges. We already talked about that over here, geometric series, right? This guy converges, but the series we're comparing to is bigger than a converging series, right? Well, I can't apply, right? I can't apply the actual convergence test to this. So I'm kind of stuck. I'm stuck here because the inequality is the wrong way for comparison. So the inequality is the wrong way for comparison, so what do, right? Well, what I do is I get another test, and it's actually what's called the limit comparison test. It'll start off the same way, but if we can't get our inequality in such a way that we can apply the direct comparison test to it, then we can use a limit comparison test. So this is where we're headed in the next video. I just wanted to mention this. I do have more examples here, but I'm going to save them for either another video or possibly in the class section.